Okay, so I want you to imagine this scenario. You're looking for places to buy and, settle down with the family, whatever, and you're presented two neighborhoods. One of them has an average income of $133,000, whereas the other one is closer to 60,000. So you're telling yourself, okay, well, currently I'm not making 130,000, but maybe in a couple of years, we're gonna be enough. We're gonna have enough to, afford the houses in this area. So let's give it a look. And then you go to this neighborhood, and you notice that most of the houses are run down and really, really, really cheap. They look like they were built 100 years ago and in bad condition. And then most of the neighborhoods aren't, well, what you would think of for an affluent neighborhood. Well, what happened here? The problem is the mean. The mean can be misleading when you have outliers. So we're going to explore this here. We have our two neighborhoods. We have neighborhood A, which is made mostly of low-income residents, but there are a few very high-income individuals that have been moving in. And in this case, it could be an early stage of a gentrifying area. So basically, high-income people move in, businesses move in, they want to revitalize the area, change it up, tear down the old buildings, and bring a new latte store or something like that, or new Starbucks. Whereas you have this other neighborhood, neighborhood B, which most residents there, they have a moderate income, and there's no extreme outliers like here. There is a more uniform distribution. So I have Python code here to run these things. I already ran them. So I have my standard imports. We're not going to go use all of them, but for this example, it's going to be NumPy and Matplotlib. So you see here we have our $28,000 to $48,000 for neighborhood A in terms of the range, and then the one person that's making $1 million, and that's why. In this case, when you're told the mean and you actually go to explore yourself, you realize it's quite misleading. Quite misleading. And then neighborhood B mean is 59,000. But then you look at the median, and the median tells you a much clearer story. It tells you that the median income is 38,500. This is like 3 times less than it's 3.5 pretty much times less than the mean. So there's a huge, massive disparity here due to this value, right? In neighborhood B, you see that the median income is equal to the mean, which is what you expect when the data is kind of evenly distributed, it's symmetric. That's something we're going to get into as well. So keep that in mind. So most residents, when they earn a moderate income, have a uniform distribution. It creates this kind of even equality between the mean and the median. Okay, so now we move over here into a actual plot that looks at this. This is a histogram. Here we have 10 bins. And for histograms, the bins are blocks, essentially, that are evenly distributed. So from here, you take the smallest value, which is 28,000, and you go to the max value, you take the difference, and you divide it by the number of bins. And then that's the bin width, essentially. So you see here, because all these values aren't like 130,000 or whatever the bin size might be, they all fall into the first bin. And then you have this huge disparity that's, this vacant space that will not forever be like this. If the area is getting gentrified, well, we would expect this to move closer to this, and then eventually move back, as it tends to happen. Meanwhile, in neighborhood B, well, I guess in this case we only have 5 bins. Let's make that 10. I think it'll be the same thing. Yeah, because they're all kind of evenly spaced, so each one has its own bin. You just have 10 bins that creates this giant rectangle, and this is not a very interesting histogram to look at. but that's just how it is. All right. In Big Bang Boom, you can see this block that really shows the evenness of the data. So basically, neighborhood A has a long right tail, right, that we see here, and that's caused by one extreme value, whereas neighborhood B is compact and centered. Using an analogy of a seesaw, right, you're at the playground, you have the big seesaw to balance yourself. Well, the mean is the balance point. And if you imagine that there's one very heavy person that's far away, well, it can shift that. It can shift that balance point, right? It's no longer at the center. It's getting pushed further back or towards that person. The median is the person who's standing in the middle of the line, right? Extreme people, they don't really affect its position. They're just there in the middle, the physical middle. And yes, when you're looking at distribution, right, for like a Gaussian or a normal distribution, the center is the mean, right? It's the place where the mean lands. But if you add skewness to it, well, not necessarily, right? The mean and the median are not always the same. So, connecting this back to like an actual real life analogy, neighborhood A, the mean suggests prosperity, but in actuality, the residents are still low income. While in neighborhood B, the mean reflects what most people actually experience. Remember that whenever you're presented outliers, especially in financial questions or things like that, take the mean with a grain of salt, because again, the wealth is not evenly distributed. For anything where you might suspect an uneven distribution, make it a point to look at the mean and the median and ask yourself, okay, well, which one makes more sense? In some cases, the mode might be more important to use as well, but I'll get into that in other videos. So, and here the mean answers a total wealth question, whereas the median answers a typical person question. So remember, neither is wrong. They answer different questions. So I hope you learned something from this. Just remember that the mean is sensitive to extreme values, and the median is anchored to position, not magnitude. And this difference matters whenever data are uneven or skewed. So thank you for listening, and I'll see you tomorrow.